For thousands of years, humanity watched the heavens in awe. They'd watch an apple fall from the tree. They'd watch the moon wander across the sky. All of these phenomena seemed unrelated. That is, until he came along. In the late 17th century, Isaac Newton proposed a breathtaking idea. Perhaps they all obey the same mathematical laws. The apple being pulled to the earth, the moon falling around the earth. His second law of motion transformed force from a vague philosophical concept into something measurable and predictable. It tells us when a force acts on an object, it changes that object's motion in a precise way. Suddenly, the flight of a cannonball, the swing of a pendulum, or the orbit of the moon, and the fall of an apple could all be understood through the same mathematical framework. For the first time, physics became a predictive science. Given the forces acting on a system, one could calculate its future. This idea powered the Industrial Revolution, a revolution that is still evolving. The universe is mechanical and predictable. The derivative as the instantaneous rate of change. Motion is about rates of change. The velocity is defined as the rate of change of position x with respect to time, and the acceleration a is defined as the second derivative of position with respect to time, or the first derivative of velocity with respect to time. Calculus becomes the language of physics under Newton. Now, Newton's second law of motion, F equals ma. In the language of calculus, this is expressed as F equals m times the second derivative of position with respect to time. This is a differential equation, and differential equations become the focus of solving problems in physics. Now, momentum, P, is equal to mass times velocity. It measures how a mass travels through space with a certain velocity. And if the mass m of an object is considered constant, then the change in momentum over time is given by the derivative of time of momentum, d by dt of p, which works out to be mass times the derivative of velocity with respect to time. And this particular derivative is also equal to the acceleration. And so by Newton's law, we get mass times acceleration, or we get force. So Newton's second law also says that force is a result of the change in momentum over time, F equals dp by dt, which expresses the idea that force determines how motion changes. Physics becomes now about solving differential equations. Functions of space and time become the primary tools for this investigation, along with vectors. And given the initial conditions and the force law, one could now calculate the future trajectory. Predictions could be theorized and tested. This was the power of Newton. Newton's laws changed the world, but they left us with a practical problem. What happens when a system becomes too complicated? A single cannonball is easy enough to calculate, but try swinging a double pendulum. Then write down every force in every direction. This quickly becomes a nightmare. Luckily, a radically different idea came along. Suppose nature has a choice. Out of all possible paths something could take, which path does it actually choose? In 1744, Leonhard Euler asked the question, how do we find the curve that minimizes or maximizes a quantity? Suppose we want to minimize a specific integral. For a path y, this integral produces a number, and for the optimal path, this integral is a minimum. This is the birth of the calculus of variations. Euler introduced the idea of perturbing a curve like the vibration of a string. So for a path y and a nearby path y plus alpha eta, its variation, this is such that for stationary endpoints, the true path has first-order changes that should disappear. And this is the basis of the calculus of variations. Euler required that the differential d by d alpha of that integral is 0, and working through the variation leads to this integral. Now this integral is treated using integration by parts, and when one uses integration by parts, this is the result. And since this must hold for every perturbation, Euler obtained that the integrand of this must be equal to 0. This is known as Euler's equation, which will later be elevated to the Euler-Lagrange equation. And that brings us to Joseph Louis Lagrange. The form Newton's equations of motion take depend on the coordinate system used, and the Lagrangian method is a reformulation, which makes it simpler to write the equations of motion in any coordinate system. This is a straightforward way to systematically handle constraints and identify conserved quantities. So we identify the general coordinate system Q with respect to the coordinate system X. And therefore we can obtain x inversely as a function of q. An explicit dependence on t in the transformation allows the possibility that q and x coordinates are related at different times. The velocity or time derivative of position can be expressed as general velocity q dot, and the chain rule gives us this expression relating x dot and q dot. Now for momentum p equals mass times velocity, in terms of the kinetic energy we can express it this way. And the generalized momentum then is this. It's the rate of change of kinetic energy with respect to velocity. By using the chain rule to relate the two, one can create a relation in Cartesian and generalized momentum coordinates in this way. Then, dx dot by dq dot can be simplified by holding q fixed, and therefore this derivative simplifies to dx by dq. And therefore we get the general momentum to be p times dx dq. And because we know Newton's force law in terms of the time derivative of momentum, taking the time derivative of the generalized momentum is given by the chain rule here. Then we introduce a slight notational change by interchanging the order of differentiation, and the second term evolves into dx dot by dq. The change in velocity with respect to the generalized coordinates. Multiplying by p on both sides, replacing on the right-hand side with d by t by dx dot, we get this equation. Thus, the equations of motion in the q-coordinate system are p dot is equal to f dx by dq plus dt by dq. The first term on the right there is called the general force, and we can just call that by some function q. So rewriting the force law with this new function q, we then begin to think about splitting the force into two parts, two components. So one part of the force is derived from the potential energy and the other from the kinetic energy. If the potential energy is given by V, then the force equated to the kinetic energy will have a little tilde over it. And if we define the Lagrangian to be the difference in the kinetic and the potential energy, L, then we can rewrite Newton's force law as follows. In terms of the Lagrangian and the new coordinate system. And the Lagrange equation of motion is therefore given here. And now what we're going to do is bring this idea together with Euler's idea, the Euler-Lagrange equation. And these are the equations of motion, or the equations of dynamics, in a generalized coordinate system. William Rowan Hamilton, 1805 to 1865, was an Irish mathematician that recognized that the entire motion of a system can be derived from a single variational statement, the variation of the action S. And this is the integral of the Lagrangian over time from one point to the next. And thus, using the variational principles of Euler and Lagrange, Hamilton elevated the action from a useful quantity to the central object of mechanics, and rather than starting with differential equations, he began with a global principle about the whole trajectory in space-time. This is the evolution of what is known as the principle of least action. By the mid-1800s, physics had become astonishingly successful. Newton gave us forces, and Euler and Lagrange described dynamics using the principle of least action. But one profound question still remained. How do objects affect each other across space? By the early 1800s, physicists had become comfortable describing forces as individual points in space. But George Green saw something remarkable. How do invisible forces actually fill the space? Instead of directly specifying a force field F, define a potential or a scalar field phi. Then differentiating that scalar field, you recover the force field. This was a novel idea, and the gradient or differential operator is used here. This operator is sometimes called nabla. Now, this idea shifts what is considered to be fundamental. The potential is primary, and the force is its gradient. Green studied equations of this form, known as Poisson's equation. It is the Laplacian of a scalar field, and it is the density of the source of the distribution. When no sources are present, we recover Laplace's equation, where this second-order derivative is equal to 0. He also introduced the idea that allows local behavior to determine global behavior through this integral equation, which is the result of assuming a force field F is the gradient of a scalar field. You see, this equation is like saying that the surface of a bubble secretly knows everything that's happening on the inside of it. Green emphasized that potentials are often more fundamental than forces, and that fields can be understood through differential equations. Volume and surface representations are equivalent. Suddenly, energy didn't only have to reside in particles. They could live in the field itself. And to describe these fields elegantly, physicists had to introduce a much more subtle concept: the idea of a potential. Michael Faraday was not primarily a mathematician. His breakthrough was conceptual. His time spent as a bookbinder allowed him to read the work of all the greats. He was a meticulous amateur physicist and chemist, and he visualized his problems with clarity. In his world, electric and magnetic effects were captured in vector fields, where every point in space has a vector associated with it. Space is not empty. It is filled with physical, invisible fields. What convinced him of this idea was a discovery in 1820 by Hans Christian Ørsted, who showed that electric currents could deflect a compass needle. In layman's terms, electricity could produce magnetism. It wasn't long before he wondered if the reverse were true. Can magnets produce electricity? In 1831, he got his answer and discovered the law of electromagnetic induction. A changing magnetic field produces an electric current. His idea revolutionized the world, and his discovery would become the basis for every modern electric generator. Michael Faraday paved the way by thinking about fields as physical objects. James Clerk Maxwell, 1831 to 1879. Maxwell translates Faraday's ideas into mathematical statements. Then he realizes flaws in Ampere's law and fixes it with a displacement current term. By 1864, Maxwell unifies electricity and magnetism, and his unification shows that light is an electromagnetic wave. Electric charge acts as a source of the electric field E, so the divergence of E is equal to the charge density over the permittivity of free space. Since there are no observed magnetic monopoles, that is, no magnetic charges, the divergence of B is equal to 0. A changing magnetic field produces an electric field, so the derivative of the magnetic field with respect to time gives us a rotating electric field. And inversely, the Ampere-Maxwell law says that we can use a current and a changing electric field to produce a magnetic field. Together, the four differential equations, given by the divergence and the curl of the electric and magnetic field, constitute Maxwell's equations of electromagnetism. They describe all the phenomena of electromagnetism. So starting with these two particular equations, we can employ a vector identity that says the divergence of a curl is equal to 0, and we can apply that to the divergence of the magnetic field. Since the divergence of the magnetic field is 0, we can assume that the magnetic field is the curl of a vector potential A. Now, substituting this into the curl of the electric field, we get the following relation. And simplifying this equation, we get the following identity. And that brings us to another vector identity, that the curl of a gradient is always equal to 0. Thus, the quantity inside the parentheses can be thought of as the gradient of a scalar potential field. So if we let that equal to the negative gradient of some scalar potential field phi, and replace that in our equation, we get this equation with a little rearrangement of terms. The electromagnetic field is described by two potentials, phi and A, the scalar and vector potentials respectively. What happens when we apply this reformulation to Maxwell's other two equations? Using the divergence of the electric field equal to the charge density over the permittivity of free space, we substitute in its new expression for E and get this equation. So now we can describe the charge density in terms of the scalar and vector potentials. The last equation, which is the curl of the magnetic field, is connected to the current J and the electric field E. Substituting on the left-hand side for B, and using some vector identities to simplify the left-hand side, we get the following result. Now there are a couple of cross terms in here that are problematic. So let's do some rearranging of terms and get this value. Now, in order to get rid of the troublesome terms, we require that the quantity in the parentheses must be equal to 0, must vanish. And therefore we are left with this identity. And one notices that this is a wave equation for the potential A. Now, after Maxwell completed his equations, he considered his equations of free space without charge and without current. And that produced a wave equation for the electric field, and one also for the magnetic field. So that wave equation said that the electric field moves as a wave with a velocity v. And he calculated this velocity to be 1 over the square root of mu naught epsilon naught. And when he actually calculated this value, miraculously it turned out to be exactly the speed of light. This was a game changer. You see, now one could think about electromagnetic fields and think about light being a part of that. Light is an electromagnetic field disturbance. It travels in waves. Now, the Laplacian operator measures how a quantity curves or spreads through space. It governs things like heat diffusion, electrostatic potentials, and gravity. It is a purely spatial derivative operator. But if a quantity also changes in time, then the natural thing to do is to add a second derivative of time. And so a vibrating string satisfies a wave equation, such as this one, or rewritten in a more familiar term as we've seen, like this. Therefore, in physics, the second derivative of space-time is given by the operator called the D'Alembertian operator, given by a little square notation. Rather than treating E and B independently, Maxwell's theory showed that the force fields could be expressed using potentials. This shift in thinking was one of the most important transitions in the history of physics. The power of potentials. The vector potential is not unique. In fact, if we take a new vector potential and scalar potential, such as these, where chi is a smooth function, well, then the observable fields, E and B, remain unchanged, or in the language of modern physics, invariant. And you see, we'll find out that this redundancy is a special kind of transformation. Now, with the success of Maxwell's unification of the electromagnetic field, Hendrik Lorentz wanted to know, why does light always seem to travel at the same speed? With Maxwell's prediction about the EM waves traveling at the speed of light, he wondered, how can every observer measure the same value of c? And that brings us to Galilean transformations in classical relativity that describe a moving observer frame of reference. In this perspective, time is taken to be the same for both observers, at rest and moving, so time is considered an absolute quantity. But when you substitute this transformation into the wave equation for the electromagnetic field, you no longer get the same equation. So to fix this, Lorentz proposed that time too must transform. So he assumed that time would transform with a small dependence on position. Since uniform motion maps straight lines to straight lines, Lorentz assumed that the following is a linear transformation. And as a linear transformation, it can be expressed as a matrix. And so we need to determine the coefficients of this matrix. And in order to preserve the fundamental measure, the determinant of this matrix must be equal to 1. So determining the coefficients. The origin of the moving frame, the primed frame, satisfies x prime equal to 0. Since the origin moves with a velocity v, we can say that x is equal to v times t. And that allows us to determine that b is equal to negative a times v. Thus we may write the moving position x as a multiple of a. So now we have this as our linear transformation. And taking the derivative of x prime with respect to x will allow us to help determine what a is, or at least its relation to the other coefficients. So dx prime by dx is given by this equation, and that helps us determine that a is equal to dx prime by dx and c is dt prime by dx. In a similar fashion, we can determine that d and b are these derivatives using the time equation. So our derivative matrix turns out to just be the transpose of the coordinate matrix. It shifts the entries of the matrix around. And so we have these two differential equations that'll now help us solve for a, b, and c, and d. Lorentz imposes the condition that the wave equation must remain invariant under this transformation, and so we must have the unprimed and primed coordinates related in this following equation. And when we substitute and expand the right-hand side of this equation, we get a quadratic with a mixed term in the middle. Now, for the wave operator to keep its form, these mixed terms must vanish, and so the coefficient of the mixed terms must be set equal to 0. And that'll give us that AC is equal to BD over C squared. And of course, by requiring A prime equals 0, and finding out that from this equation we get B equal to negative AV, we can then make that substitution into this equation. And simplifying some terms, we get C is equal to negative VD over the speed of light squared. So in our moving frame, we have these two equations governing the motion. And in order for space and time to be scaled consistently, we must take A and D to be equal in transformation. So if we let that constant just be named gamma, we have this as our coordinate transformation matrix, and all we need to do is determine gamma. Now, if we impose that the determinant of this transformation has a value of 1, then this equation gives us a way of solving for gamma. And gamma turns out to be 1 over the square root of 1 minus v squared over c squared, also known now as the Lorentz factor. He laid the groundwork for special relativity, but it would take another man's vision to consider that time physically transforms this way. So the true power of the potential is not merely that it generates fields. It exposes an underlying symmetry. The math simplifies, and it hints that the fundamental laws of nature have less to do with forces and more to do with geometry. Henri Poincaré, between 1904 and 1905, notices something profound. After coining the term Lorentz transformation, and letting lambda be a Lorentz transformation, he observes that composing two Lorentz transformations together produces another one. He recognizes that this forms a group, a mathematical group he coins the Lorentz group lambda. And he identifies the invariant quantity x squared plus y squared plus z squared minus c squared t squared, which remains unchanged under every Lorentz transformation. Now, symmetry becomes the underlying principle of organization, and group theory enters the physics game. He was the first to recognize that Lorentz transformations form a mathematical group, and they preserve Maxwell's equations. They express a new principle of relativity and looked as a true symmetry of nature. 3 years later, after Einstein published his results, Hermann Minkowski looked at Poincaré's invariant and said, "This isn't just an invariant, it's a distance." Minkowski realized just as rotations preserve the quantity x squared plus y squared, Lorentz transformations preserve this quantity. He reinterprets the Lorentz group as a group of rotations in four-dimensional spacetime, with the metric being given by this quantity. This becomes a key bridge from special to general relativity. The ordinary derivative tells you how something changes from one point to the next, assuming that that's possible. And usually it is, because we're working with a flat space. But on a curved surface, a curved space, the ordinary derivative fails. It doesn't pick up the information that the curvature adds to the situation. And so we need a new type of derivative, one called the covariant derivative. Albert Einstein, 1905. His special theory of relativity. The laws of physics are the same in all reference frames, and light moves at a constant speed c in every reference frame. He asked the question, how do we know two events happened at the same time? Instead of asking how Maxwell's equations transform, he asked what the universe itself must be like if Maxwell's equations were correct. From these principles, he recovered the Lorentz factor, 1 over the square root of 1 minus v squared over c squared, also known as gamma. And from that, he derived the concept of time dilation, length contraction, and the relativity of simultaneity. Lorentz believed that these equations describe matter moving through the ether. Einstein realized that they describe space and time themselves. That distinction changes everything. The laws of physics should look identical to every observer moving at a constant velocity. Special relativity describes observers moving at a constant velocity. Therefore, it is a theory of light and of observation. Things in the universe, though, accelerate. Gravity exists, and matter responds to space-time. So Einstein wondered, can an accelerated observer be described by exactly the same laws? And then Einstein would have what he called the happiest thought of his life, the equivalence principle. It's the idea that gravity and acceleration appear to be locally indistinguishable. And all of this led to his formulation of what is now known as general relativity. Gravity creates curved surfaces. And in order to compare two vectors at different points on a curved surface, i.e. in a gravity field, Einstein needed new mathematics. In 1912, Einstein was directed by a close friend and colleague, Marcel Grossmann, to the work of Riemann, Ricci, Christoffel, and Levi-Civita. And Einstein learned the mathematics of tensors. On a flat surface, two vectors can be compared by subtracting them. And thus ordinary calculus allows you to compare nearby vectors through that subtraction. On a curved surface, however, on a curved manifold, those two vectors belong to different tangent spaces. You see, vectors live on tangent spaces. So the problem is, vectors belonging to different tangent spaces on a curved surface cannot geometrically be subtracted in any meaningful way. So this requires the covariant derivative, a derivative that respects the effects of a curvature given by a surface. And instead of the ordinary derivative, the covariant derivative includes a connection term. Here for gravity, the connection term is called the Christoffel symbol. Given by the gamma symbol there, provides the Levi-Civita connection coefficients that account for the curvature in the metric. They are the connection coefficients that tell how to compare vectors from point to point. This connection in general relativity provides a torsion-free connection, and it tells space-time how to rotate vectors while moving from point to point. Now, if one considers two different paths, x mu and x nu, and we repeat the two paths in an opposite order, if space is flat, then taking the covariant derivatives in either order doesn't matter. But in a curved space, it does. The order in which you differentiate will pick up the curvature of the space given by the Riemann curvature tensor. It measures the curvature of the manifold or surface by parallel transporting a vector around a loop on this manifold. And if the vector returns rotated, that rotation is a measure of the curvature of that surface. And for curved spaces, this is exactly what Einstein needed to describe gravity. Now, in 4 dimensions, the Riemann tensor has 256 components, but applying symmetry reduces the number of independent components to 20. And through a tensor process called contraction, contracting the Riemann tensor produces the Ricci curvature tensor, which is a similar curvature object. Here, r mu nu is the contraction of the Riemann tensor, and it captures the part of the curvature directly related to how matter focuses or refocuses nearby geodesic paths. The Ricci or average scalar curvature is obtained by applying an inverse metric to the Ricci tensor, which produces the Ricci scalar r, also something very necessary for Einstein to describe gravity. From this, Einstein developed his tensor describing the effects of gravity g mu nu as r mu nu minus 1/2 r g mu nu. And this combination satisfies the following relation, and the right side gives the stress-energy momentum tensor content of the curved spacetime. Einstein's reformulation of gravity with tensors that use the covariant derivative fundamentally changed the way physicists approached non-Euclidean geometries. It would set the stage for what would later become a gauge theory. This approach to geometry gave physicists a new tool to explore the nature of forces. It especially caught the attention of another prominent mathematician of the time. Einstein had shown that gravity wasn't a force in the traditional sense. It was geometry itself, and that idea carried a lot of weight. Hermann Weyl, 1885 to 1955. Geometry fascinated him. He studied under David Hilbert, who encouraged his students to seek the deepest possible principles rather than isolated problems. He became captivated by the work of Bernard Riemann, Felix Klein, and Sophus Lie. And his biggest question would be, could physics simply be geometry? That single question guided nearly everything he did. When Einstein published General Relativity in 1915, Weyl was astonished. Einstein had shown that gravity was not really a force, but instead the effect of geometry, the geometry of space-time. For Hermann Weyl, this was revolutionary. But Weyl noticed that general relativity contained one piece of geometry that seemed, well, a bit arbitrary. The length of vectors. His criticism was that Einstein's theory says that after transporting a ruler around a loop, its direction may rotate because of the curvature, but its length remains fixed. Weyl wondered, why should nature preserve length exactly? Rotation depends on path. Why shouldn't the scale also depend on path? In 1918, Weyl had a great idea. He proposed that every point in spacetime should be free to choose its own unit of length. Instead of the metric being the only geometric object, he introduced another field which tells neighboring observers how to change their measuring sticks. So instead of preserving the covariant derivative of the metric being equal to 0, he proposed a non-zero derivative for the metric, in other words, a metric that changes, calling it non-metricity. And he labeled the field a mu, a gauge field, which means the calibration field. Now, Einstein had an objection to this. Einstein immediately realized something troubling about Weyl's idea. You see, if Weyl were correct, then the frequency of atoms would depend on the path they had taken through spacetime. Two identical clocks traveling through different routes would return permanently altered. In other words, atoms would continually change their spectra. But this does not happen experimentally. Einstein's criticism was devastating. Weyl's original theory had failed. This did not defeat Weyl. He simply considered, maybe I chose the wrong thing to transform. Hermann Weyl kept working. At first glance, the covariant derivative looks nothing more than a mathematical correction, but hidden inside that correction is a profound idea. The 1920s brought a revolution unlike anything physics had seen before. Instead of particles following precise trajectories, nature was revealed to be governed by a wave function, probabilities, and the strange mathematics of quantum mechanics. Hidden within this new framework was a remarkable symmetry. The overall phase of a quantum wave function could change without altering observable physics. This simple idea transformed symmetry from a mathematical curiosity into a fundamental principle, opening the door for an entirely new understanding of the forces of nature. In 1920, Erwin Schrödinger introduces wave mechanics. Quantum mechanics was born. Matter was described by a wave function, psi of x. Weyl noticed something remarkable about the wave function. Multiplying the wave function by a factor of e to the I theta, which is a complex phase factor, nothing observable changes. The overall phase factor is arbitrary. This looked exactly like the freedom he had been looking for in geometry. Except it wasn't length, it was phase. In 1929, Weyl's breakthrough was letting phase change locally from point to point. He proposed the following. Instead of g mu nu changing in this way, he proposed the wave function be transformed. But an immediate problem arises. Ordinary derivatives no longer transform correctly. The solution, just as with a changing geometry, was to introduce a connection term, analogous to what Einstein did with general relativity. Weyl introduces a new covariant derivative, shown here. The gauge field now compensates for the changing quantum phase. And from this, electromagnetism emerges naturally. Weil had done it. Weil discovered something profound. Local symmetries require a connection field. A local symmetry cannot exist by itself, and demanding local symmetry forces the existence of a compensating field. That single principle eventually led to electromagnetism, the weak and strong nuclear forces, being connected to gauge groups. In 1954, Chenin Yang and Robert Mills asked a very bold question. What if these internal symmetries weren't just simple phase rotations? What if they were something richer?
I think I was very, very fortunate. I had earlier referred to the fact that the paper I wrote for my PhD thesis under Teller was about using symmetry, the concept of symmetry, and group theory in mathematics to apply it to natural phenomena. For some reason, that was something that I already when I was in China was very much interested in. I was very fortunate that I got onto this track or this particular aspect of the structure of physical laws that early. So when I was a graduate student in Chicago, beyond that paper that I just referred to about, which became my thesis, I studied the question of symmetry. And in particular, one important mathematical expression of symmetry was called gauge symmetry or gauge invariance, which was invented by a great mathematician named Hermann Bayer in 1918. I was hooked on that idea. So as a graduate student, I scripted some notes. And these notes I found a few years ago in my papers, and so they have now been republished. If you read those notes, you see that I was trying to say maybe this gauge symmetry idea could be used to generate a theory of how these elementary particles would interact with each other, what forces they exert on each other. So that key idea I already had. But to implement that, I got stuck. So I would work on it for a few days and abandon it. But then after 2 years, there were more elementary particles found. There were more desire to study how they relate to each other, how they interact with each other. So I would come back to this idea and then got stuck again with the implementation. This took place several times until 1954. In 1953, I was already at the Institute for Advanced Studies for several years, and the Brookhaven National Laboratory had a new the world's largest accelerator at that time called Cosmotron, just beginning to operate. They want to get some young theorists to help the experimentalists there. So they asked me to visit Brookhaven for 1 year, 1953 to 1954, which I did. And they assigned a small office for me, and they assigned the office mate, and that turned out to be Bob Mills. Bob Mills was some 4 or 5 years younger than I, and he was just about to get his PhD, and he got a job as a sort of a pre-PhD postdoc at Brookhaven. So we shared the office, and of course we began to talk about the various aspects of physics. I found him to be very intelligent and with wide-ranging interests. So naturally, we began to discuss this unfinished idea. about how to use gauge symmetry to create the interactions between particles. And then we got stuck at the same place when Bob and I years later recalled we were both vague about what precisely happened. But we said apparently that the reason that it doesn't work is because a fundamental formula which we copied from Maxwell may need some amendment. So let's add a term to it and see what happens. We added a quadratic term. We found that all the difficulties disappear. All these very complicated formula, which became longer and longer, all cancel each other out, so that we got very beautiful, compact equation. So we knew we got something. Then there was a long struggle because the idea was beautiful. The structure was very beautiful. But how do you compare that with experiments? And there was one major problem which we couldn't solve, namely, according to what we structured, it was a set of equations. It apparently gives zero mass particles, lots of them. But there were no such zero mass particles to be found. So that was a big obstacle. In fact, in February 1954, while Mills and I were still doing this, Oppenheimer, back in Princeton, heard about it. And also Pauli was visiting Princeton, and Pauli was interested in the idea. So Oppenheimer called me up and said, "Frank, why don't you come back to Princeton and give a seminar on what you're doing?" So I did. And at the seminar, Pauli gave me a hard time because he was interested in it, and he also knew that the idea would produce massless particles, which were not experimentally found. So he kept on raising this question. So I had described that experience in my selected papers. After that, for some 4 months, Mills and I tried to solve this problem. We couldn't. But we felt that the idea was very beautiful. So we wrote a paper discussing this particular question. Why are there massless particles? Why we apparently were creating a theory with massless particles which were not experimentally found. That section was very difficult to write because we didn't know what the solution was. But today, with hindsight, if you read that section, what it essentially says is that there cannot be massless particles. So there must be something in addition, which we do not know. So we ended the paragraph in that note. Of course, now it has become a very important paper because later on there were additional ideas, very important ideas, called the symmetry breaking, which became very successful starting in the 1970s.
Consider a base space M, a spacetime manifold, with a point P on it. In general relativity, the curvature of the base manifold is connected to the tangent space through the Levi-Civita connection, where the base field is governed by the metric g mu nu. The complete set of all tangent planes at all points on the manifold M is called a tangent bundle. It is the internal space that governs the action on the manifold. The curvature of the field, that is spacetime, is described by how the Riemann curvature tensor acts on vectors. given here below. In the case of the base field being the metric tensor, the Levi-Civita connection connects the rate of change of the metric with respect to different directions. And this is how we define the Levi-Civita connection, otherwise known as the Christoffel symbol. The covariant derivative of a one-form, a nu, using this connection would be written as follows. And lower indices here transform antisymmetrically, introducing the minus sign you see there. The force of gravity is the result of the connection acting on something in the field. Here, the gravity field is the product of spacetime manifold being measured by vectors living in the tangent space. Weyl's idea was to apply to each point on a spacetime manifold a gauge field A mu, which provided a connection to the local symmetry demanded by an arbitrary phase rotation of the wave function psi, which under such transformation keeps the physics invariant, gauge invariant. His idea was to multiply by a factor e to the I theta, being a phase factor. And this is simply just a rotation around a circle in the complex plane. The symmetry group of rotations on a circle is called U1, or the unitary group. So what is the unitary group? It is the set of all complex numbers with unit magnitude, so one can define that set here. But since every complex number of unit length can be written as z equals e to the I theta, then we can define U1 as the set of all e to the I theta, where theta is a real number. Geometrically, this is just the unit circle in the complex plane. As a group, the group operation e to the I alpha times e to the I beta, we notice that angles simply add. Both addition and multiplication here are commutative. And if we notice that, because of the circle, theta has periodicity, group closure is encoded in this periodicity. Any element differing by a multiple of 2 pi is the same group element. So what is unitarity? A matrix is unitary if U dagger times U is equal to 1. The matrix U dagger is the conjugate transpose, which would mean that the conjugate transpose is given by the generator E raised to the negative I theta. Every complex number of unit magnitude is automatically unitary. So unlike discrete symmetry, theta can vary continuously, therefore U1 is a continuous Lie group. Its manifold is simply S1, the circle, and every Lie group has generators. For U1, everything commutes. Thus, e to the I theta is the only generator of the group. Electromagnetism only has one gauge field and thus one gauge boson, a force-carrying particle, associated to it. That boson is the photon. Now let's talk a little bit about Lie algebras. Take an infinitesimal rotation, theta equal to epsilon, where epsilon is very small. By expanding it out, the Lie algebra therefore consists of the imaginary numbers I times the real numbers. And since there's only one generator, the commutator is equal to 0. Thus, U1 is an abelian group, and this will later translate into the idea that there is no self-interaction with the gauge field. Now suppose a quantum wave function, psi of x. If we multiply psi of x by a phase factor of e to the I theta, since only the norm squared is observable, nothing observable actually changes. Therefore, nature possesses a global U1 symmetry. Now from that gauge field, one can define a curvature, or a field strength tensor, defined here. And this is precisely the electromagnetic field tensor, and inside it lives the electric and magnetic fields, shown here as a matrix. One notices that this matrix is anti-symmetric. And one also notices that this is traceless. Electromagnetism appears naturally from demanding U1 local symmetry. Gauge fields have curvature associated to them. That curvature describes its field strength. The gauge groups associated with these gauge fields form an internal symmetry space, which is analogous to the tangent space of Einstein's theory. In physics, the communicators of these forces are called bosons, gauge bosons, and so we will call them force-carrying particles. They communicate information to and from particles that experience forces. They have interaction with the force carriers. Gauge fields tell us about how forces act from point to point, i.e., locally. So what kind of internal symmetry space is created by gauge groups, and how are they similar to tangent spaces? Consider a base manifold M to be spacetime, and two different points on this spacetime manifold. Assigned to every point is a fiber, or in this case a circle or a gauge space. The internal symmetry space is called a fiber, and it is analogous to the tangent space in Einstein's theory. The set of all fibers on the base manifold is called a fiber bundle, analogous to the tangent bundle. So it is the space where the symmetry takes action. And it takes action through the covariant derivative. Now imagine a field on our manifold psi, and Weil in 1929 said the wave function psi is defined on this base manifold, and given a fiber bundle G, at each point on the manifold the wave function is evaluated. It takes on its value in the output space of the fiber bundle G through its gauge connection A mu, and the covariant derivative D tells you how to move from point to point. So the group symmetry actions happen in the fiber bundle. The wave function is therefore a section of the fiber bundle. It assigns one vector or complex number in the fiber to every point in space-time. The elementary particle revolution. What if the idea of gauge symmetry or local symmetry, invariance, isn't unique to electromagnetism? That's what Chen and Yang wondered. The newly discovered strong and weak nuclear forces behave nothing like electromagnetism. Protons and neutrons were held together by some other mechanism. A simple phase rotation wasn't enough. If local symmetry explains electromagnetism, why shouldn't every fundamental force also arise from local symmetry? What would happen if the quantity we're rotating isn't just one complex phase, but an entire vector space of internal states? So instead of just making one phase translation, he proposed that every point in space have its own internal coordinate system. That is, that the phase angle depends on position x. With U1, there's only one generator. It is both a local and a global symmetry. But now with theta being position dependent, under his proposal, we must now use matrix-valued elements. So the unitary group of 2x2 matrices, known as SU2, the special unitary group of 2x2 matrices, is used to describe this gauge field. Under his proposal now, since we are now changing from a scalar multiple to a matrix-valued quantity, the symmetry group that we are working with as our fiber is no longer abelian. Non-abelian because the matrices do not commute. So why choose the Lie group SU2? Well, it works nicely for protons and neutrons, also known as nucleons. This comes from physicists noting that protons and neutrons have nearly identical masses. They interact almost identically under the strong force, and Heisenberg proposed that they were two states of the same particle. Just like the electron was shown to have two spin states, the same was first assumed for nucleons, and that became referred to as isospin. And so it was described beautifully by the SU2 group. The big question became now, how do these non-abelian gauge groups behave? And what is the result of having a non-abelian gauge group? SU2 has three generators, sigma 1, 2, and 3, which are the Pauli spin matrices. They represent three independent directions or degrees of freedom in the group's internal space. By replacing the single phase with a matrix rotation, the group element now looks like this, where G is the interaction strength or the coupling constant, theta is the position-dependent rotation parameter, and T is a generator of the symmetry group. And the three generators are connected to the Pauli spin matrices. The generators do not commute. Therefore, the commutator is not equal to 0. As you might recall with the Riemann curvature tensor, the field strength comes from the covariant derivative, and the cleanest way to define this is through the commutator of the covariant derivative. Now, expanding the field strength tensor, we pick up an extra term in the field tensor, meaning that the gauge field interacts with itself. That self-interaction came from demanding local symmetry. The three generators of SU2 correspond to the three independent directions of weak isospin symmetry. And unlike the electromagnetic field mediated by the photon, these gauge fields appear in their own field strength tensor. That extra term means that the force-carrying bosons also participate in the interaction. Yang-Mills' theory showed us that non-abelian gauge groups are much richer in content. Generators can correspond to conserved quantities. The three weak gauge bosons are the W plus or minus and the Z naught bosons. The gauge group SU3 was later found to govern the strong nuclear force, with its 8 generators corresponding to the 8 strong bosons called gluons that are responsible for holding quarks together, quarks being the building blocks of protons and neutrons. These three gauge theories unify all three ideas into what is called the standard model of particle physics. Murray-Gell-Mann was essential in putting the SU3 piece together. Still, a new problem became obvious, one raised by Wolfgang Pauli during a seminar. The SU2 theory predicts massless bosons. experiments show that these bosons acquire a mass. When one examines this, there's a problem. The Yang-Mills action has no mass term present in it, yet masses are acquired somehow. And this is known as the mass gap problem, and is one of the Clay Institute for Mathematics Millennium Problems, worth $1 million. It's that important. By 1954, physicists had discovered a remarkable pattern. Symmetry dictated geometry. Geometry dictated the connection, and the connection dictated the covariant derivative. But one question still remained. What equation should these fields, these fiber bundles, obey? The answer would come from an idea we've been quietly carrying with us since Euler and Lagrange. That concept is action. The Lagrangian. Classically, the Lagrangian is the kinetic energy minus the potential energy. But in a field theory, we use the Lagrangian density with a curly L. It is chosen to be the simplest Lorentz invariant, gauge invariant scalar built from the gauge field that leads to local, second-order field theory with the correct dynamics. These are the 5 requirements: a Lorentz scalar, gauge invariant, local, produces sensible equations, and has the correct mass dimension, meaning that the theory is renormalizable in 4 dimensions. Can we just use the gauge field potential itself for the Lagrangian? Well, let's look at how it transforms. Because of that second term, it is not gauge invariant, so it cannot appear as the kinetic part of the Lagrangian. The field strength tensor is gauge covariant, given by the covariant derivative defined there. When one expands the commutator of the covariant derivative, one gets the expansion for the field strength tensor. If we expand this out in generators, again for the gauge field given here and the commutator of the generators, we can expand this out as follows. We have the commutator of the gauge fields here, and so the part of the term in the field tensor that gives us interaction terms can be evaluated. In component form, we have the field strength tensor here, and thus we can expand it out here. So in terms of the components of these generators, we can now determine how the curvature transforms, looking at the transformation of the covariant derivative commutator. And so what does this show here? Well, right now this just shows that our field strength tensor is covariant, but not gauge invariant. So we therefore need to combine 2 field strengths in a way to remove the u's in the expression. So we need to construct a gauge invariant scalar. And that means we are going to try to find the field strength by taking the trace of the field strength squared, which will produce a gauge invariant. So why a quadratic? Why squared? I mean, we could try a linear trace of the field strength, but it's not a Lorentz scalar, and so we retain 2 indices. So then one would next try a quadratic. And the trace of the quadratic, well, this checks all the requirement boxes. It makes the simplest non-trivial choice. The higher order choices, although gauge invariant, introduce higher order corrections. So it meets all of these requirements, 1 through 5. So now that we have our gauge invariant, for the Yang-Mills Lagrangian, one asks what is the analog of Maxwell's theory once the gauge group is non-abelian, and we take a look at the Maxwell action shown here. The Maxwell action is then replaced with the Yang-Mills action. The natural generalization is to simply replace the EM field strength with the non-abelian one and take the trace, again because we're working with matrix-valued quantities. And using the convention that the trace of the generators is equal to 1/2 delta AB, we get the action to be equal to -1/4 times the integral of the square of the field. One notices that also that there are no mass terms in this Lagrangian, which makes it gauge bosons theoretically massless. So we can examine this structure more closely if we define the tensor G mu nu upper A to be that part of the field strength tensor. And so expanding out the Yang-Mills Lagrangian to a few orders of magnitude, the Lagrangian contains the kinetic term plus these extra terms, so it contains 3 gauge boson interactions and 4 other gauge boson interactions. Except, again, no mass term appears. Classically, Yang-Mills theory is a massless theory. Gauge bosons are predicted to be massless. Unique to non-abelian gauge group theories, these expressions tell us that the gauge bosons themselves become sources for other gauge bosons. And after quantization and applying the path integral formalization, we can examine the energy eigenstates given by the Ket notations, Ket 0 through Ket 3 and so on, with associated energies, E0, E1, E2, E3 and so on. We call the vacuum state Ket 0, and the first excited physical state, Ket 1, with energy E1. So a mass gap is defined as the difference in the energies E1 and E0. We'll give that the designation of delta. If delta is greater than 0, then there are no physical excitations of arbitrary low value. That is, there exists a minimum value for the ground or vacuum state. Here's the thing. Nonlinear quantum interactions are expected to produce a delta greater than 0. And using the relation E equals mc squared, the lightest observable particle has a mass gap value of delta over c squared. It's explaining this that is core to the Millennium problem. You see, mass emerges dynamically from the quantum theory. The Clay Institute of Mathematics offers a Millennium Prize for 7 problems, this being one of them, worth $1 million if solved. The way that they state the problem on their website is, prove that for any compact simple gauge group G, a non-trivial quantum Yang-Mills theory exists on R4 and has a mass gap of delta greater than 0, existence including things outlined in the paper. They basically want you to show that the theory exists mathematically and that it possesses a positive mass gap. The gauge invariant states is what this is really about, the spectrum, and not necessarily the gauge fields themselves. Every generation rewrites the mathematics of nature. not because nature changes, but because our understanding does. And with that, thanks for watching.